In the last segment, we talked about what a pure bending is, what an impure bending is, and we discussed about the canonical configuration which is used to represent a pure bending. In this segment, we will talk about some assumptions or the conditions under which the situation of pure conditions will be there, not only with respect to the forces or the moments that we apply, but also with respect to the geometry of the beam which is subjected to the force. And that is and before I go to that, if you remember, in axial loading we had this condition that it's a prismatic bar, the area of cross section doesn't change throughout the length, and the forces were acting like that, and the assumption that over any cross section the stresses were uniform, the normal stresses were uniform, constant, right. So, and we assumed in a way, or if we impose the condition that F should be applied as uniformly as possible over the cross section, so that we will have this condition as close to the end as possible. Otherwise, if we apply this concentrated force, so the stresses will not be uniform here and they will gradually become uniform, and we have to be far away, means we have to be far away from both the ends to have these conditions of uniformity of the stress. And similarly, when we went into the torsion case, we said that the shear stress distribution cannot even be assumed to be uniform, and we figured out that it varies from center where it is 0 to the maximum at the circumference. But there one more assumption was that for pure bending, our cross section must be an axisymmetric section, right. So, the most general thing will be of an annular cylinder. So, this is what we can get at max, and the torque obviously was acting like that, okay, and the stresses were not uniform, but they were varying over this cross section. They were varying not like that, but like that, okay. So, they varied like that, the tau, the shear stress. And here also this torque was assumed to be the force which was causing this torque, if they were uniformly distributed over this all the area of cross section, it's this distribution of linear distribution will happen as close as possible to the ends. So, that now in comparison to that, we should discuss now the cases for bending, so that it will be clear that where, under what situation, what sort of conditions or assumptions are required to create a pure case of a particular loading. Now, in case of bending, you have the prismatic bar whose area of cross section should have a plane of symmetry like this, suppose, and here what I have assumed is, which is not very apparent in the drawing, So this is a plane okay, which crosses this prismatic bar at the center, and this cross section, if I draw like this is the cross section of the bar. It's symmetric about this plane. So if I draw this view, say this view, if I draw, it will look something like this. I'm drawing isosceles trapezium to tell that most generally it can be like that, okay, and you can have a rectangle, you can have a square, but there are special cases of this isosceles trapezium, and this plane of symmetry is somewhere here, okay. So this is the first geometric requirement for a pure bending to happen or to prevail in a particular beam. Then, so this was about the geometry. Now what about the loading? The loading is, when I said that this is the most general, no, it's not the most general. A more general case could be even like this. It could be anything. This is a representative thing. Sorry for that, using that word, that this is the most general. For example, I can just choose, which is very common, say, sorry, I want to say this, like this, now this is a cross section which has a clear symmetry about this plane. Now if you extrude this cross section throughout, again this is a case where you expect that a pure bending to exist, okay. So please do not, when I said that this is the most general, no, it is the easiest shape to draw, where we can show that the section has a symmetry about a plane and which is not a rectangle, okay. So that's the thing. Otherwise it can be any general shape, yeah. And now about the loading, the moment which we are applying on this beam must exist on this plane only. That means if I extended this plane to draw only, okay, because this is anyway an imaginary plane only, there is no such physical plane which is existing, and then I should apply my moment on this plane. So here, okay, so the moment that I am applying, these are existing on this blue colored plane, okay. So that's very important, because that means the loading also is symmetric with respect to this cross section. That means these M's are acting here, okay, on this plane M. Fine, okay. And so I can just draw one more picture from looking from this side so that it will be clearer maybe. So this looks something like maybe this is the beam, and I'll draw even this blue colored plane, imaginary plane. This is not a physical plane, and the moment which exists on this plane, okay. And this sense of the moment is conventionally taken to be positive. That's it. Now this is the assumption. Any more? I think that should be fine. Now, if so geometrically and load wise we have considered all the conditions or assumptions which are required to create a case of pure bending. Then we will talk about I don't know, I'll talk about the deformation which are caused by such a case of pure bending in the next segment. Okay.